YouTube channel. In this video I am going to explain you about Gauss law, derivation of Gauss law in integral and differential form. Before going to start, if you are new to my channel, please subscribe my channel for upcoming videos. Okay, let us try to solve the Gauss law in integral and differential form. So Gauss law applies to any arbitrary surface enclosing a charge or charge distribution. So as we know, first you need to understand the fundamental laws of electromagnetism. So Gauss law is one of the very important uh, law applies to arbitrary surfaces which encloses charge or charge distribution. So any imaginary surface enclosing a charge or charge distribution, we call it as a Gaussian surface. So we usually choose the Gaussian surface so that our calculation become easier. So first we need to understand the statement of Gauss law. It states that the total electric flux through any arbitrary or any imaginary closed surface S, which is called Gaussian surface, is directly proportional to the total charge capital Q enclosed by the surface. So first you should understand the statement clearly, then we can write the equation for that. So electric flux, as we know, E dot ds. Electric flux is what? Number of lines passing through particular area. So the total electric flux through imaginary closed surface is equal to what? The total charge we call a summation of small q is given by total charge capital Q. So Q divided by epsilon naught. So this is the equation for the statement of Gauss law. So here SI unit for according to the statement, which is equal to 1 divided by Q epsilon naught, and the net charge is the algebraic sum of all charges enclosed within the surface. That is capital Q is what? Summation of small q. Then let us find out whether this equation 1 applies to any arbitrary surface enclosing a point charge. Okay, so for that we have to consider here a closed arbitrary surface which encloses a point charge in free space. So imagine that is enclosed within the Gaussian surface, that is arbitrary shape. So we can understand with the help of this diagram. This is the diagram for Gauss law for a point charge enclosed by an arbitrary surface. So here is the charge Q enclosed within the Gaussian surface. So in 3 dimension we have taken it x, y, z coordinates, and this is the arbitrary surface. We are going to choose here the small area ds, which makes angle theta with respect to small charge E. With that, if we draw the perpendicular lines, that is given by the direction of field, and ds, small elemental area. So from figure 1 we have chosen the origin of the coordinate system to be at the location of the point of the charge, and P be a point charge on the Gaussian surface having the position vector. So we choose a small element of area that must be, as I said, centered at point P, that is denoted by ds. So electric field at point P, how we will write? In the previous video I have explained about electric charge and field. You can just go to that video. So field is given by if we understand Coulomb's law, you can write the equation for field. So E is equal to 1 divided by 4 pi epsilon naught at point P. We are writing. So Q divided by R square unit vector R cap. Then we can just write R cap is what? Vector R by R. So this is equation 2. Then element of electric flux passing through, we have taken small area ds from arbitrary surface. So electric flux is what? Number of lines passing through particular area. So within this ds, the flux passing through is given by this equation. So E dot ds. So first we have to write the equation for field at point P. Then flux equation we have to write. That is in terms of E dot ds, because we have taken elemental area small ds. So 1 divided by 4 pi epsilon naught Q divided by R cube. So we need unit vector we have written. So R cube vector R ds. Next, after writing field equation, flux, as we know, the equation for flux is equal to E dot ds. So if we substitute field, electric field equation at point P, then you will get equation 3. So next, as we know, we have taken a small elemental area ds. So it makes an angle with respect to point P. Then, so theta is the angle between vector R and ds. Then R dot ds, if we take that is dot product R ds cos theta. You also know from vector algebra that the projection of P along ds, we know that the quantity this ds cos theta divided by r square. If we modify equation 4, we will get ds cos theta divided by r square. That is equal to, here when it makes an angle with respect to point P at origin O, then it will make an angle that is called solid angle subtended at ds by an elemental area. Then ds cos theta r square divided by is equal to what? That is given by solid angle. So here the solid angle is defined at origin O, the location of the charge. Then as we have earlier written equation 3, that is for flux. In that, what you have to do? You have to substitute the r ds cos theta divided by r cube by solid angle d omega. So we will get the equation 6 Q divided by 4 pi epsilon naught d omega. The total electric flux through the surface S is determined by, if you want to get the total flux, you have to integrate equation 6. So E dot integral of E dot ds is equal to, that you will get total flux phi E is equal to integral E dot ds equal to Q divided by 4 pi epsilon naught integral of d omega. We have taken surface area. Now, since the surface S surrounds the point O and the total solid angle, we have the solid angle, as we know mathematically, integral of d omega is equal to what? 4 pi. If we substitute this in equation 7, we will get here the total flux E dot ds is equal to Q divided by epsilon naught. 4 pi get cancelled here. So here, suppose that instead of a single charge at center of the sphere, many charges are situated in some region of space. Then the principle of superposition, we know that the sum of individual charges, the electric field due to sum of the individual charges, E is equal to summation j of vector Ej. By definition, the electric flux through a closed surface that encloses all these charges is given by, we have written equation for single point charge. If we have number of charges, then we will have the field for each individual charges, that is given by principle of superposition. Then from equation 6 and 7, for individual charge we have written, if we have a set of charges, then we can write this equation 6 and 7 as that is given by summation of charges qj. J may take the values of integral values 1, 2, 3 and so on. Then this integral, that is flux, is equal to what? 1 divided by 4 pi epsilon naught summation j qj for number of charges. Q enclosed is the total, or capital Q is what? This small summation of small q is represented by capital Q. Q is the total or net charge enclosed by the surface S. We can replace here a small summation of Qj by capital Q. Then we can write equation 8 as follows. So here E dot ds is equal to what? Qj by epsilon naught. Okay. Then equation 9, which is we have arrived at the statement of Gauss law, as we have stated the Gauss law, that is total charge enclosed within the surface is equal to what? The flux flowing through the surface. So equation 9 is what? Integral form of Gauss law, or else we can write this as the integral form. Then we can arrive at differential form of Gauss law. Equation 9 tells us that the flux of the electric field through any surface would be the same regardless of its shape. So it is proportional to charge enclosed is the integral form of Gauss law. So we can write Gauss law in differential form using divergence theorem. So as we have here integral of E dot ds, that is surface integral, we can convert it into, if you want to write in differential form, surface integral to volume integral. That is called Gauss divergence theorem. So del dot E dV, if we convert surface to volume integral, then we get volume charge density. So as we know here, the capital Q is what? Total charge, that is equal to volume charge density rho into dV. Now you may recall the divergence theorem from given as E dot ds is equal to 1 divided by epsilon naught. Wherever capital Q is there, you can replace it by integral of rho dV. We substitute the value of the equation in this left hand side by equation 10. So E dot ds is equal to what? Differential form we have to write, and then this differential form is equal to what? 1 divided by epsilon naught rho dV. So equation 12 gives Gauss law in differential form, that is del dot E is equal to rho divided by epsilon naught. It is easier to apply Gauss law in its differential form. So however, that we have expressed it only for volume charge density, since the integral form of Gauss law can be applied to point or line, surface and volume charges. So these are some of the applications of Gauss law. So this is all about derivation of Gauss law in integral and differential form. I hope this video is helpful for you. If it is helpful, please like, share and subscribe my channel. Thank you for watching.